So what do we learn first about astronomy and cosmology? First, we learn about what is luminosity and radiant flux intensity. Yeah? So what is luminosity? Luminosity is basically the total power output of radiation emitted by a star. Because you know the star is like the sun is a type of star, or not type, it's a star. So therefore fusion will take place at the surface, then they will emit all the radiation, right? So total power emitted is called your luminosity. All right. So the unit for luminosity is watt, because it's actually power. Okay. But what is radiant flux intensity? Radiant flux intensity is the intensity detected at the Earth due to that star. Like for example, the total power output of the sun is called luminosity, but the amount that reaches the Earth that we can detect is called radiant flux intensity. But we are not using power, we're using intensity. So if you remember in AS, intensity is defined as power per unit area or energy per unit time per unit area. So that is called radiant flux intensity. So that means it's not just power, it's power per unit area. So remember, so the unit will be watt per meter squared. So if you want a diagram or picture to help you imagine like this. So this is the star. This is a total energy per unit time emitted. This is energy per unit time per unit area detected at the Earth. You understand? That is radiant flux intensity. But the good news is the formula is very simple one. Between the two, it's something like your formula for intensity in waves on AS. I'll show you how. Now, you remember, right? We said that radiant flux intensity is total energy per unit time per unit area. And total energy per unit time is basically the power of the sun. All right. So the power of the sun divided by the surface area where it reaches the Earth. So you take the power of the sun, which is the luminosity of the sun, you divide by the surface area. Now, how do we calculate the surface area? Now, the logic is like this. When the sun emits this energy, all right, in the form of EM radiation, the energy was spread out like a ball. From the sun, it spreads out like a ball. So basically, the power divided by the surface area of the ball that it spreads to, that is your area. Then you get your intensity, right? So what you will do is you measure the distance between the star and the Earth. Then the power of the sun will be spread over a sphere with this radius. Correct not? It will spread over a surface area of a sphere with this radius. So you take the luminosity L and they divide by the surface area of a sphere. So surface area of a sphere is 4 pi r squared. So the r here is the distance between the Earth and the star. That's the formula. Easy, right? Radiant flux intensity. All right, it's just like a lamp producing the light, power over the area, surface area of the sphere where the Earth is. That's it. Okay, this formula very important. Must memorize. Yeah. Okay. I under the new syllabus, if you want to see what equations are given to you, right? Because there'll be new topics, right? Okay, you can actually refer to the specimen here. Because only the specimen paper will show you the new formulas. So the specimen paper, wait. They only show you a few formulas on here, like that on here. Isn't it bad? So few only. Is that missing a page on the specimen paper? Okay, but anyway, don't know whether you can trust or not. They'll give you one page only, or like that only, which is fewer than what they gave you last time. Last time, they at least will give you the formula for AC. This one don't have already. Okay, I don't know lah. Maybe like this. Yeah.
But in the March paper, got 2 pages.
The March paper. That's why the specimen paper cannot trust. Okay, let's look at the March paper lah. Because the March paper will be the more accurate one. Fortunately, we're having the March paper. Otherwise, we will die. Because you know why? We wouldn't know what formulas are given also. Well, Cambridge also, you see the specimen paper, so half cooked one. All right, so here got, oh yeah, they're missing one page lah, the specimen paper, which is this lah. That's why we saw up to here. The specimen paper, I think got printing error lah. But you see, this radiant flux intensity not given. What is given is Stefan Boltzmann law and Doppler redshift. All right, so it's not given. So I don't know, that's bad news for you a bit. So no formula for that. So you got to memorize yourself. Okay, so remember this formula. Okay, next one. By the way, if they ask you what assumptions are made, right? Specimen on the CIE website got 2 pages. So why the specimen paper only got 1 page? I also took from CIE website. Maybe I took it when it was fresh. So that means they probably forgot to upload one and they corrected it. Okay, fine. Okay. Maybe they corrected it once the discount. I downloaded quite early. Because whenever they announce the change to syllabus, I straight away go and download it. Okay, but anyway, doesn't matter. Now we know. Right. So what are the assumptions made, right, for this formula? The assumption is that the luminosity is constant. That means the power produced by the star is always constant. Now, is that true? Over a long period of time, of course, the sun will slowly die out. All right. But for the time period where we're doing the experiment, it shouldn't drop. It should be constant. Because it's not going to die very quickly. It takes many billions of years to die, just like our sun also will die in a few, I think, few 100 million years, a few million years. All right. So, but anyway, we'll all be dead by then. So luminosity is constant, and we assume that it follows the inverse square law. That one okay no problem. And from this diagram, you will see that the further away you are from the star, the smaller the intensity you will reach which is why, right, if you are in Mercury, right, because Mercury is the first planet or the closest planet to the solar system, right? So it will have the greatest intensity. Greatest intensity. So what is the temperature at Mercury? I remember was few hundred degrees Celsius. So you cannot survive there. As a comparison, Pluto is the furthest planet, but again, planet or subplanet or dwarf planet, don't care. Pluto is so far away. The temperature there is negative 223 degrees Celsius, right? So you can see that the further away you go, the smaller the intensity that reaches you. That's why it's colder, right? It makes sense on you. Right, next formula. Okay, let's talk about what is standard candle first. Now, standard candle definition, you must know. So the definition of a standard candle is this: an astronomical object that has a known luminosity. Now, actually, for 1 mark, you can just write the first sentence here. But I'm just concerned, right, that if the question asks for 2 marks, then I give you another detail. Due to a characteristic quality possessed by that class or object. Now, what does that mean? It's a bit confusing, right? Now, standard candles are what the astronomers they can calculate, right? What is the actual luminosity on it? So how do they know the luminosity? They have some calculations. Number one type of standard, the 2 types of standard candles that the astronomers use. One is a Cepheid variable star. So this Cepheid variable star has a unique characteristic in the sense that it become brighter, less bright, brighter, less bright, like a pulse like that. So when you're observing the star, it's like pulse. It's not like constant brightness. It'll be bright, then less bright, bright, then less bright. And the period, right, how long it becomes brighter, less bright, brighter, less bright, whether it's fast or slow, will determine the luminosity one. So that one they can calculate. Okay, so don't worry lah. The formula is not our syllabus lah. So, but based on the period, they can calculate the luminosity. Okay. Another type of standard candle, which the astronomers know the luminosity, is a type 1a supernova. So this supernova, again, right, every time you see a supernova in a distant galaxy, that luminosity is always the same. All supernovas have the same luminosity. So why do we want to know all these things, right? Now, based on what we just learned previously from this formula, now think carefully, right? If we always talk about, not we lah, all these nerds, they always say, oh, this galaxy is how many like million light years away from the Earth, and then another galaxy is how many million light years from Earth. So how do they know all these galaxies, right, in the universe, how far they are away from the Earth? Is from here. Because if they can detect, right, a supernova or Cepheid variable star in that far away galaxy, then they will know the luminosity, right? And then they'll try to detect the radiant flux intensity at the Earth coming from that supernova or coming from that specific variable star. So once you know the flux intensity that we detect here, and you know the luminosity there, you can actually substitute and find the distance between the Earth and that galaxy. So that's how astronomers can estimate how far the galaxies are away. Because I think the most recent news I read was they discovered a planet in a different galaxy, which is very close to the conditions on the Earth, right? In the sense that the temperature, the distance is quite similar. The mass is also quite similar. So meaning to say it could hold life. So meaning to say that one day we can always go and shift there when the Earth is destroyed. But few million light years away. So I don't know whether it works or not traveling so far. Okay, but anyway, that's a different story. But that's how they actually use standard candles as a distance indicator. This is what I'm trying to teach you. Okay, first section done. Second section is on Wien's displacement law. I will finish up the whole chapter, so then you can do the questions I want to. Those are all related one. Now, Wien's displacement law tells you about the relationship between the wavelength of the radiation emitted from the star, the relation between that wavelengths and also the temperature of the star. So we know that different stars have different temperatures, right? Some stars are hotter, some stars are colder. So how do the astronomers know that temperature of the star is how much, that temperature of the sun is how much? Because even they know the temperature of the sun. How did they know? It's not like they went over there and measured the temperature using a thermometer. You cannot. So how do you know the temperature of the stars and stuff like that? So according to Wien's displacement law, the wavelength with the highest intensity will be inversely proportional to the surface temperature of the star. So what does that mean, right? Now, all stars, right, will emit a range of EM radiation, right? But the wavelengths, right, that are emitted, they don't all have the same intensity. Some wavelengths have lower intensity, some wavelengths have higher intensity. So they measure the wavelength that is producing the highest intensity. That wavelength that produces high intensity. Can you see this graph is intensity versus the wavelength? So let's say you're talking about a star with 6,000 Kelvin. A star with a surface temperature of 6,000 Kelvin, this is the distribution of wavelengths. That means this is the EM radiation emitted, but the wavelength that has the highest intensity is this value. So you can read, so it's about within the yellow color. But if let's say you have another star that is colder, let's say at 4,000 Kelvin, the distribution of the wavelengths will be here. And you will notice that the wavelength that produces the highest intensity is longer than the wavelength. And if it is even lower temperature, the wavelength that has higher intensity is also higher wavelength. So in other words, the hotter the star, the wavelength that produces the highest intensity will be shorter. And see now, as you go higher temperature, the wavelength will be shorter. The one that, but we're not talking about any random wavelength. The wavelength that is producing the highest intensity, that wavelength is shorter. Do you understand? So because of that, right, when you look at the star, right, they have different colors. For us, we all look as if they're same color, right? But astronomers with the correct telescope, they can see different colors. All the stars in the sky, they have different colors, depending on the temperature. So the hotter the star, the yellower the star will look. But the cooler the star, the redder the star will look. You understand what I'm trying to say? Because the highest intensity is yellow, means you see predominantly yellow. So it's a bit yellowish. But if the temperature is lower and your majority of wavelength is within the red color wavelength, then you see it's a bit redder. All right. So that's the relationship between the color and the wavelength and the temperature. So when you say inversely proportional, there's a formula So lambda max times T equals a constant. So your lambda max times T is a value here, 2.9 times 10^3. Now, how do we use this formula? Very simple one. Let's say they give you a temperature of the sun and you know the lambda max. Lambda max doesn't mean the maximum wavelength produced. No. Some people thought it's a maximum wavelength produced. No, it is the wavelength that is produced with the highest intensity. You understand? Of course, there are other wavelengths as well, but the wavelength that is emitted with the highest intensity is lambda max, not the highest wavelength. All right, don't confuse that. So let's say they give you the lambda max for the sun, the temperature of the sun, and then they tell you that astronomers are observing another star in the universe, and the lambda max is a different value. Then you can actually use this formula to calculate the temperature of that star. Either you use ratio lambda 2 T2 equals to lambda 1 T1, or if they're kind enough, they just give you this formula, then you just substitute a lambda and find the temperature. It's very fixed. Do you understand? So there are actually a few conclusions that can be made. Oh yeah, just now didn't we say that there is the Wien's displacement law formula given to you? Or no, Stefan Boltzmann. So it's not even given. So you don't have to memorize this constant. You can just remember lambda max times T is a constant. So you can use this relationship, okay, between the stars. So conclusion, number one, the shorter the wavelength at peak intensity, the hotter the star tends to be. So it's whiter or bluer towards the shorter wavelength. Remember, violet, indigo, blue. So we say it's a bluer star. But cooler stars tend to be a bit reddish or yellowish. All right. And also the intensity of the radiation at each wavelength is greater. Now, what do I mean by that? Can you see that overall, right, lower temperature stars, the graph is flatter. Higher temperature stars, the graph is sharper. That means that at all wavelengths, there's higher intensity. That means more photons are being produced by hotter stars and fewer photons are produced by cooler stars. That means some hotter stars not only are bluer, but it's brighter as well. That's what it means. Cooler stars are not only a bit yellowish or reddish, but it is also less bright. So there's a relationship between intensity and the temperature of the star. So if you look up into the sky, the brighter it is, chances are temperature is also higher. But of course, I cannot just conclude like that because it also depends on the distance. Yes, if you are saying two stars with equal distance to the Earth, like one from this galaxy, one from that galaxy, but equal distance, the brighter one should have the higher temperature. Okay. And these are basically a bit of example. You don't need to memorize. They're just trying to show you above 33,000, you'll be like bluish color, the star. And then as you go down the temperature, it will become reddish, the star. And then in between, all this. So these are super high temperatures one, just to tell you. Okay. And the next one, Stefan Boltzmann's law. What formulas? Okay. This one talks to you about the luminosity. So remember the luminosity, the question, how do they know the flux without knowing the distance? Oh, the flux intensity is what we detect. So the telescope will capture the light entering it, and that's how they measure the radiant flux intensity. So radiant flux intensity is something that we can measure because it's the intensity of the light. That's why we can measure. Okay. Right, the next one, the star's luminosity depends on two factors. That means how bright, right, or how much energy that they actually release, right, depends on two things. Just now we said surface temperature, right? Not. There's another thing I want to talk to you, which is the radius of the star. So it seems that when the star is larger, that means logic is if the star is larger, got more surface area. More surface area means more light can be emitted. That's the logic, right? Not. Because you're talking about total power only, not power per unit area. So the bigger the star, the more power it can emit. So there's a formula here, which is the total luminosity is 4 pi r squared, where r is the radius of the star and T is the temperature of the star. So the hotter the star is, the greater the luminosity, that's what I told you. But the bigger the size of the star, the bigger the luminosity also. But you need to make an assumption. This formula is actually for a black body, Now, when you say black body, they're not being racist, they're not saying Africans or whatever. The black body here is referring to a body that will only emit radiation and absorb radiation 100%. That means it will not reflect on. So for example, if let's say you take a normal ball, you shine a torchlight onto the ball, the light will reflect and come to your eye. So that one, the one. A black body, you shine a torchlight, the light will disappear. That's a black body. And if let's say you can see any light coming from the ball, it means the ball itself is producing the light. It's not reflecting the light to you. That is a black body. All right, that's a black body. So we are assuming that all stars are black body. Okay, all stars are black bodies. That means any light coming from that star is purely coming from that star. It's not like some other light coming from a distant star reflect and coming to you. No, okay, that's just the assumption. Okay. So finally, I'm going to conclude how we use, that's why all the formulas are related. We can actually calculate or estimate the radius of the star. So sometimes, right, they will tell you, or that star is how big, that star is how big, right? How do they even know that? Okay, I'll show you. Remember I told you, if we look at a Cepheid variable star, or let's say the supernova, you know the luminosity and the flux intensity, you find the distance, right? Or the other way around, let's say you know the flux intensity and you know the distance, you also can find the luminosity, right? Okay, but usually no, usually we find the distance, so if you want to. But you also have lambda max is inversely proportional to temperature. So in other words, if we can measure the spectrum, right, of the light arriving from a distant star to us, of course using telescope, not using your eye. So then they will break down the wavelengths, right? They see what's the maximum wavelength. Then they can conclude the temperature of the star, correct or not? Because it is always a constant, lambda max times T. So since they know the temperature of the star and they know the luminosity, so I told you normally you are supposed to already know luminosity of a standard candle, but if it's not a standard candle, then we must know the distance, okay? So basically that one, they didn't tell us how, maybe they give but they will give in the question the distance. So let's say you know the flux intensity and they give you the distance to the star, then you find the luminosity, right? Substitute the luminosity, substitute the temperature, then you can find the radius of the star. So they can play around with the formulas, but all the formulas are basically related. That's why I just want to show you the summary. So these are your three formulas. Okay. So what's good? Okay, now one last formula. Actually, two last formula. One is Doppler redshift. Okay, now, if you still remember the Doppler effect in your AS, what was the Doppler effect? The Doppler effect is basically when the source is moving towards us or away from us, we are the observer, but the source is moving away or towards us. The frequency that we observe will change, right? That's the Doppler effect. Okay, and that's why you learn about if the source is moving away from us, then the frequency will be lower. Coming towards us, the frequency will be higher. Remember that part in our AS. In fact, in AS, they even give you this formula, which also seems to be the same formula they give you in the data sheet for your new syllabus as well. But this formula actually is not used for light one. Because you know why? This is more general, like a car coming towards us, the sound that we hear and stuff like that. In your AS, we use this formula for light as well, for stars and all that. But actually, it's not correct one. Because this formula is only applicable for like small objects and the speed is relatively low. But for bigger objects and like stars moving away from us, they're so much bigger, right? And the speed is also much bigger also. We don't usually use this formula, all right? But the same basic principles will apply. So what is the same basic principle? I'll show you. Let's say the star is stationary, okay? Now, the star will produce all the light, okay, coming out from it. So you should see the whole visible light spectrum, right now. But remember how absorption spectrum works, I taught you under quantum physics. Surrounding the sun or even the star is a layer of relatively cool gases. So you got hydrogen, helium, all the different types of gases, which are not undergoing fusion. That's why we say relatively cool gases. So when the photons, right, passes through these gases, if the photon energy matches the energy needed for the electrons to jump to a higher level, remember they will absorb the photons, right? So when they absorb the photon, they'll jump to a higher level, and then they become very excited, they fall back down. When they fall back down, they will produce back the same photons, re-emit back the same photons. But what happens is they will scatter it randomly. That's what we learn in absorption spectrum. It means if you have the star here, you have the Earth here, the gases are around here. So by right, all the radiation should reach the Earth. But the gases absorb that photons and scatter it in all directions. So that means it took all the photons supposed to reach the Earth and scatter it. That's why the amount reaching the Earth is very little. And that's why you see the dark lines right now. Remember we said the dark lines are due to that. I'm just revising on it. So if they know, right, the dark line pattern, they can tell you what gases are absorbing the light. Because like in the lab, right, if you pass white light through hydrogen gas, you get 4 dark lines. If it passes through helium, you get a certain number of dark lines, right? So when they're observing, right, of course not us, the astronomers observe using the telescope, they will select a particular absorption spectrum. So they say they select this absorption spectrum for hydrogen or for helium, then they compare it to the lab. Because if white light passes through helium, these are the positions of the dark lines. But the light from the star passing through helium, the dark lines all shifted a bit to the right. Let's see, shifted the right. So like, for example, this is from this distant galaxy, BAS 11 now. Okay, not bus number 11 now. This is name of the galaxy. So they noticed that all the similar line patterns, same, but all shifted to the right. So what does it mean? That means that star is moving away from us, because longer wavelength means shorter, smaller frequency. Because the wavelength is longer, the black lines have shifted to the right means more red. More red means longer wavelength. So longer wavelength means smaller frequency. Smaller frequency means away from us. So they can tell you the galaxy is moving away from us. But of course, that is not enough. They want to calculate how fast that galaxy is moving away from us. There's a special formula, this one. So for A2, we don't use this formula anymore. For AS, you can use this formula. For A2, for stars, we use this special formula. How you derive, don't have to know. They got special way of deriving. But this is also Doppler effect formula, but specially for stars. So what does delta lambda over lambda, delta F over F, and V over C mean? Like for example, if you pick one wavelength here, this is the original wavelength when the star is not moving, or when the source of the light is not moving. This is a wavelength. But from that galaxy, shifted to here. So this is the new wavelength. This dark line shift to this position. So you measure this wavelength, you measure this wavelength, the difference in the wavelength is a delta lambda. You understand? But you divide by your original wavelength, or you can do delta F over F. That means instead of taking wavelength, you measure this frequency, you measure this frequency, you minus, that's a delta F. Then you divide by this frequency also can. So the formula is either delta lambda or delta F or F also can. So that will be equals to V over C, where V is the speed of the source moving away from us. That means the speed of the star. Recession means going away from us. The speed of the star moving away from us is called speed of recession over the speed of light. So this is how they calculate how fast the stars are moving away from us based on the absorption spectrum from that star. So they see how much the absorption spectrum for a certain gas like helium or hydrogen for that particular star, the absorption spectrum, how much it shifts. And then they can tell you how fast that star is moving away from us. Makes sense or not, guys? Okay, so but this one not given, is it? I can't remember. Was it given?
Sir, is it always moving away or
got given? Yeah. Why always moving away? This is related to our next part, Big Bang Theory. Okay, so it's always moving away, but good news is the formula is given. Okay, so now how do we actually, why are we here? Okay, so why are they always moving away? Because of the expanding universe. This is Big Bang Theory. So of course, if you believe in God, if you're religious, of course you don't believe that everything happened by chance. You always believe that God created. But whether you believe or not, the Big Bang Theory doesn't matter. You just do it for the sake of exam. Nobody's asking you to change your religion or belief system. It doesn't matter. Personally, I also don't believe in Big Bang Theory. I still have to teach you. All right, so if you were to blow up a balloon, and before you blow up the balloon, you make dots. use marker pen and put dots, right? Then you blow up the balloon. As you blow up the balloon, the dots will separate. So that's what they want you to imagine the universe is behaving. The universe keeps expanding. Now, why does it keep expanding? Because scientists believe that the universe started with a big bang. That means everybody was just like in one small space, then boom, explode. So when they explode, they spread out. That's it. And because they spread out, everybody is moving away from everybody else. So if you look at any star that is far away from us, they're all moving away from us. And not only are they moving from us, from this formula, they also concluded that the further away the star is from us, the bigger the redshift. That means the faster they're moving away from us. That means the stars nearer to us are moving away from us at a lower speed. Stars further away from us are moving away from us at a higher speed. So that is the idea behind the Big Bang Theory. But based on the Big Bang Theory, they actually predicted the age of the universe. That means how many years ago was the universe created from the Big Bang? Okay, so they can predict lah. Okay, so how they predict, I'll show you how lah. I already told you that the further away the star, right, the faster they are moving, right? So there's this relationship called Hubble's law. It says the recession speed of galaxies moving away from Earth is proportional to the distance. So the further away they are, the faster they're moving away. So they get V equals H naught times D. How did they know this? They plotted a graph. Because they observe, right, the stars, the distance, the further away they calculate the V. Because I told you, my delta, lambda, or lambda, or delta, F, or F, you can measure, okay, by observing the absorption spectrum. Speed of light is fixed. So based on different stars, at different distances, they can calculate the speed of the stars. So then what they did was they plotted a graph of the V versus the distance. Then they noticed a straight line through the origin. Okay, they plotted all the points here, then they got a straight line to the origin. And then they did experiment to calculate the constant, and they end up with this, V equals to H naught times D, where H naught is your Hubble's constant. Okay, but how do we actually calculate the age of the universe? Must wait for the tutorial. Okay, but it's basically using this. Okay, that's all our Big Bang Theory. Okay,